All right, kiddos, so this is going to be your day 3 of Unit 3 video. And what we're going to talk about is what a special angle is, what a non-special angle is, and how we make trig calculations using non-special angles and ratios. Okay, so first let's talk about special angles. Okay, so special angles have been all those nice, cute, start here. So 30 degrees, and then you've got 45 degrees. And then after that, you have got 60 degrees, right? And then, of course, you also had 0 degrees, and right here, you have 90 degrees. Okay, so these were the special angles that we've been using so far, and these are called your quadrant 1 special angles. Okay, and you'll see why here in a second. Anyway, so we have a little definition here that you can go ahead and use to answer EQ1. So what is a special angle? Well, a special angle is an angle that's rational and has a rationally expressible trigonometric ratio. That's a mouthful to say, isn't it? But all I'm really saying is, so 30 degrees, right? A 30-degree angle has first of all, it's rational. Okay? Second of all, if I take the sine of 30 degrees, right, I'm going to get 1/2, which is also rational. If I take the cosine of 30 degrees, okay, I'm going to get square root of 3/2. And this isn't technically rational because this square root of 3 here isn't rational, but it is expressible. It is expressible as a ratio of the square root of 3 to 2. Okay, so that's what we mean by rationally expressible. Okay, what about the tangent of 30? Well, same idea, square root of 3/3. Okay, so 30, therefore, by this little definition, and it took me a while to come up with this, 30 is a special angle. Okay, now let's talk about non-special angles. So this is the main thing that we're going to concentrate on in this lesson today. Okay, so a non-special angle, and actually here, before I get a little too crazy, let me back up. So let's go ahead and talk about quadrants, as I said earlier, and let me show you a little bit of what I mean. Okay, so I've got a 30-degree angle again. Okay, and my cosine of this 30-degree angle, it would be square root of 3/2. And my sine would be 1/2. Okay, so cosine, sine. Now, what if I made this angle larger by a lot? What if I took this guy and let's say I put it way out over here, okay, in a way such that this angle here is still 30 degrees, right? But this actual angle that we're looking at, the actual angle would be 150 degrees. Forgot to put the 1. Okay, so this would also be a special angle. Okay, it would have a rationally expressible trigonometric ratio for sine, cosine, and for tangent. So, for example, the cosine of this guy would be negative square root of 3/2, and the sine of this guy would be positive 1/2 still. So it would have the same sign. Okay, so let me go back to what I was talking about with quadrants. Okay, so this would be quadrant 1, right? Just like on our Cartesian coordinate system, right? This would be where x and y are both positive, or where cosine and sine are both positive. Okay, here in quadrant 2, however, we have cosine and sine, except cosine would be negative, or our x would be negative, and our y would still be positive. Okay? So that means if the pattern continues, and we'll learn a lot more about this here in the weeks to come, but here in quadrant 3, well, that means my cosine would still be negative, and my sine would be also negative. Okay? And over here in quadrant 4, that means my cosine would become positive again, and my sine would stay negative. Okay, so those little Cartesian plane rules, they still apply when we're talking about angles, and we'll learn a lot more about that coming up soon when we get into radians and the unit circle. Okay, so back to this planet. So EQ2, what is a non-special angle? So we saw the special angles. They have trigonometric ratios that are rationally expressible, and they themselves are also rational. Okay, now let's look at our definition for non-special. So non-special is basically, I'll just say basically the inverse of special angles. Okay, so if the angle itself is irrational, or if it doesn't have a rationally expressible trig ratio, then it's not a special angle. So for example, let's look at a 20-degree angle. So let's say this is a 20-degree angle right here. Okay, so if I have a right triangle, and this particular angle is 20 degrees, right? What would its trig ratio be? And let's say this side length right here, let's say this hypotenuse, or actually here we'll use the leg. Let's say the leg is 1. Okay, and this guy here is unknown, and we'll go ahead and call this guy just M, is also unknown. Okay, so if I do the tangent of 20 degrees, it would be equal to opposite over adjacent. Okay, and what would end up happening, if I cross multiply, I'm going to get tangent 20 equals 1 times y. So at this point, I don't have a table to look at, okay? But what I can go ahead and tell you is that this side y right here would be approximately 0.37, okay? And what does that mean? Well, I would have 0.37 to 1. So this is a completely irrational number. I can't express it as anything, okay? And I cannot express this trig ratio rationally the same way I could with these angles here, with these nice, cute little, square root of 3 to 2, 1 to 2, and so on. Okay, so this would be, 20 degrees would be a non-special angle. Okay, so everything that doesn't have a rationally expressible trig ratio, or if the angle itself is irrational, and we'll see an example of that here in a second, then it's not a special angle. Okay, so how do we make trigonometric calculations with non-special angles and trig ratios? Kind of like what I was able to do here, right? The tangent of 20 degrees ended up being approximately 0.37. Okay, how did I do that? Well, there's a number of ways to do it. You could do it the way that Ptolemy did, who was an ancient Greek mathematician of Alexandria. And he dedicated his entire life to making a table of sines, cosines, and tangents, and their inverses. And astronomers used it for some 1,000 years, for an entire millennium, right? And all the tables that followed afterwards that, famous scientists like Albert Einstein and Stephen Hawking used, they were all the result of his work. Okay, and what he did was basically just do very, very, very precise estimations of what they would be, right? He didn't really get the exact measurements, but he did the best that he could. Okay. Another way to look at it is to look at it with calculus using an infinite series called a Taylor series. Okay, and you have no idea what this is, and I'm not even going to try to explain it to you. And if you just look at, some of this monstrosity right here, you'll learn how Taylor series work when you get into calculus. But right now, let's not even bother about it. Okay, and the last way that we're going to look at it is by using a computer algorithm, a very special computer algorithm called a CORDIC algorithm. which stands for Coordinate Rotation Digital Computer. Okay, so what an algorithm is, so for example, I'll give you a very basic example of an algorithm. If I wanted to multiply 25 or 24 times 12, right? We have a set process by hand that we can use to calculate this. 2 times 4 is 8, 2 times 2 is 4, 0 for a placeholder, 4, 2, and then we add 2, 8, 8, right? This is an algorithm. It's a procedural program, if you will, that's followed in order to attain some calculation or some result. Okay, so that's what an algorithm is, and that's what computers and phones and everything, they all use. It's how they all work. It's how AI works, all of that stuff. Anyway, a very simple algorithm, at least for a computer, can get very, very, very highly precise calculations as to what trig ratios and their inverses would be if you have a non-special angle or non-special trig ratio. Okay, and it turns out that that very algorithm is on your phones in the calculators that you use on them. Okay, so we're going to go ahead and use that, and I'll probably make a different video to kind of go over how you're going to use your phone to do trig. Okay, because it may be a little difficult. I'm definitely going to talk about it a lot in class. And trust me, you're going to get plenty of practice. So don't worry. Okay, just follow along. So here we have a trigonometric equation, and it's going to give us a non-special trigonometric ratio. So let's go ahead and solve it. So I'm going to bring this out here. So 3 sine theta plus 2 equals 3. I'm going to subtract 2 from both sides. That's going to give me 3 sine theta is equal to 1. Divide by 3 on both sides. That's going to give me sine theta equals 1/3. And there it is. If you look in your trig table, there is no trig ratio for sine of 1 to 3. Okay, so we're going to go ahead and take the arc sine of both sides. And this is going to give us our missing angle theta. And really, it's going to give us an estimation of it. So if I use I'll use a phone calculator. Or actually, no, I won't, because that'll take too long. I'm going to have to just use a separate video to go over how that's going to work. But I'm going to do the arc sine of 1/3. And that gives me an angle of about 19.47 degrees. Okay, so let's try it again. So I've got 16 cosine squared theta equals 5. I'm going to divide by 16 on both sides, so that's going to give me cosine squared theta equals 5 over 16. Take the square root of both sides, and I'm going to bring my work over here. Take the square root of both sides, I'm going to have cosine theta is equal to the square root of 5 over 16. And remember, we have a quotient law of radicals as well, right? So the nth root of a over b is the same thing as the nth root of a over the nth root of b. Okay, so I can rewrite this as square root of 5 over square root of 16, which of course is equal to square root of 5 over 4. So now I'm going to take the arc cosine of both sides. And what I do to one side, do the other. And throw that in the calculator, and we'll get an estimation of our, what do you call it, missing angle. And we get approximately 56.01 degrees. Okay, let's do one more example. This guy here, so 4 tangent 4 times theta, all of that over 5 is equal to 1/3. Okay, so I'm going to multiply by 5 on both sides. That's going to give me 4 tangent 4 theta is equal to 5 over 3. Then I'm going to divide by 4 on both sides. That's going to give me tangent 4 theta is equal to 5 over 12. Then I'm going to take the arctangent of both sides. And that's going to give me theta. Oops, not theta. What's wrong with me? It's going to give me 4 theta is equal to the arctangent of 5/12. Okay, and go ahead and throw that in the calculator. So arctangent of 5/12. That gives me approximately, let me bring my work over here. That gives me approximately, so 4 times our unknown angle theta is approximately equal to 22.62 degrees. And we're still not done yet. We still need to divide by 4 on both sides. And that's going to give me my missing angle is approximately, divide that by 4, 5.65 degrees. So it's a really skinny angle. Okay, so nothing really changes. All we're doing now is using the calculator. So let's go back to what we've been calling one of the special angles, or one of the special triangles, I'm sorry. So this guy is a 3, 4, 5, right? And we were told its angles are 37, 53, 90. Now, you may also remember that I told you guys it's not precisely 37 degrees, it's approximately 37 degrees, and it's not precisely 53 degrees, it's approximately 53 degrees. The 90, of course, is exactly 90, otherwise it's not a right triangle. Anyway, let's go ahead and figure out exactly what these two angles would be. Okay, so if I set this up as a trig problem, so I'm going to go ahead and say the tangent of theta 1 is equal to opposite over adjacent. I had a brain fart. So opposite over adjacent. So that means this angle here, theta 1, is equal to the arctangent of 4/3. And of course, this isn't the only way I could have done it. I could have done the arc cosine of 3 over 5. I could have done the arc sine of 4 over 5, right? Whatever. Tangent is usually easier for me. Okay, so let's do that. So arctangent 4/3, we get, well, something that we already knew, approximately 53.13 degrees. Okay, so if I go ahead and do the math for theta 2 right here, okay, and I'm going to use the arc sine. I'm going to use the arc sine, or here, before I do that, so let me set it up. So sine of theta 2 is equal to 3/5, which means theta 2 is equal to the arc sine of 3/5. Okay, so let's go ahead and do the math for that and see what theta 2 is. So theta 2 is approximately 36.87 degrees. Oops. Okay, so this guy is approximately 36.87 degrees, and this guy here is approximately 53.13 degrees. Okay, so now we know exactly what they are. Okay, now these aren't exact. The exact measurement of the angle theta 2, in this case, the exact measurement is the arc sine of 3/5, or 0.6, right? And the exact measurement of theta 1 was the arctangent of 4/3. Okay, so that's us putting it to work on actual triangles. So now let's apply what we've learned so far on a whole bunch of other examples. Okay, and to keep this video short, I'll probably just do example A and D. Okay, anyway, so if this angle here is 35, that means this angle B is exactly 55. Okay, all the same though, those are not special angles. Okay, so I still need to find A and hypotenuse C. Okay, so let's go ahead and find A first. So tangent 35 is equal to opposites over adjacents. So that would be A over 6. Okay, I can still treat this as a proportion just so I can get A by itself. I can go ahead and say it's tangent 35 over 1 is equal to A over 6. Okay, cross multiply, that's going to give me 6 times tangent 35 is equal to 1 times A, which is A. So A is by itself now. Now I'm just going to throw this stuff in the calculator. So if you're using your phone calculator, you're going to hit 35 and then hit the tangent button. So tangent 35. And then you're going to multiply by 6. And that gives you that A is approximately 4.20. Okay, so A is approximately 4.2 in length. Okay, well, what is our hypotenuse C? So for C, I'm going to go ahead and use cosine because I haven't used cosine yet in this video. So why not? So cosine of 35 is equal to 6 over C. And again, I want to put cosine of 35 over 1 so that I can cross multiply. So 6 times 1 is 6. C times the cosine of 35 is C cosine 35. Divide by cosine 35 on both sides. And I'm going to get C, or 6 over the cosine of 35 is equal to C. Okay, so in your phone calculator, you're going to have to do some copying and pasting. Okay, and if you don't know how to do that, I'll be able to help you in class, in tutoring, or, you know, hopefully the video I make will work. But the only thing is I only have an iPhone. Yeah, I'm not one of those guys that has like several different kinds of phones. Anyway, so 6 divided by cosine of 35 gives us our missing hypotenuse C, and it is approximately 7.32 in length. Okay, so nothing, again, nothing really changes. Nothing really changes. We're just using our calculators now. Okay, and I'm going to use something with a little more contrast. Let's see, I'll use green. Okay, so now this one's a little different than what we saw here on triangle A. So on triangle D, we don't know any of the angles except our right angle, of course. We don't know theta 1 or theta 2. Okay, so what does that mean for us? Well, that means we need to calculate the angles. Another thing that's goofy is we don't know all 3 sides. We only know 2 sides, so we're a little restricted. Okay, so I'm going to go ahead and calculate theta 1 first, and I'm going to use sine. So the sine of theta 1, and I'm doing triangle D, the sine of theta 1 is equal to 15 over 40. And I'm going to go ahead and reduce that just so I have smaller numbers. Reduce that by 5. That's going to give me 3 over 8. Okay, so theta 1 is equal to the arc sine, because I take the arc sine of both sides, right? And I'm not showing that step because it seems a little tedious. Like we should have that down by now. But anyway, so the arc sine of 3/8. That's going to give me that theta 1 is approximately 22.02 degrees. And again, we always round to the nearest hundredth. So this guy is approximately 22.02 degrees. Now, there's 2 things we could do to calculate theta 2. We can use arc trig, like I did just now, or theta 1 plus theta 2, they should add up to 90 because this guy here is 90, which means all 3 would add to 180. So knowing that, let's work smart and not hard. So I'm going to do 90 minus, and I'm going to copy and paste our 22.02 blah, blah, blah. And that gives me that theta 2 is approximately 67.98 degrees. Okay, so now we know both of our angles. Okay, so now I can calculate this missing side x. Okay, and I'm going to continue using theta 1 just for funsies, and I'm going to use cosine. So I'm going to say cosine of 22.02. And again, you want to be copying and pasting if you can help it. Okay, don't use these decimal estimates, or use a decimal estimate, but go at least like 4 or 5 decimal places. So that way it's really, really precise and close to what it should be. Anyway, so cosine of 22.02 is equal to adjacent over hypotenuse. Put this guy over 1, cross multiply. That's going to give me 40 times the cosine of 22.02 is equal to our missing side x. And that's what I'm just going to throw in the calculator. So 40 times the cosine. I'm going to copy and paste here. It's going to give me, it's approximately 37.08. Okay, so this missing side here, approximately 37.08 in length. Okay, so again, for the sake of brevity, if you need more examples or any more help, obviously, you know I'm here for you. So we answered all 3 of our EQs. We talked about special versus non-special angles, and we saw how to make trig calculations using non-special angles and non-special trig ratios. All right, kiddos, so that's it for this video. If you need any other help or anything, come through tutoring. Let me know in class. Otherwise, goodbye.